Our planet, Earth, it seems so solid beneath our feet, a steadfast foundation for our cities, our homes, our very lives. Yet this perception of unwavering stability is, in a cosmic sense, an illusion. The Earth is a dynamic entity, constantly shifting, ever-changing. Deep beneath the surface, immense forces are at play. These forces shape continents, raise mountains, and carve out oceans. They are the architects of our world's grandest features. But they also hold the power to unleash unimaginable devastation. Megaquakes are not a matter of if, but a matter of when. They are an inevitable consequence of living on a geologically active planet, a world that is very much alive. Imagine the Earth not as a static ball of rock, but as a living, breathing organism. Its crust, the very ground we walk on, is broken into giant pieces. These pieces are always moving, albeit incredibly slowly. They drift, they collide, they grind past each other. Most of this movement is imperceptible to us in our daily lives. We go about our routines, unaware of the titanic forces building up pressure miles below. But every now and then this accumulated stress reaches a breaking point. The release is sudden, the release is violent, the Earth trembles, and sometimes it unleashes a megaquake, an event that can redefine landscapes and challenge civilizations. The concept of an inevitable disaster can be unsettling. It speaks to forces beyond our complete control, yet understanding this inevitability is the first step towards wisdom and preparedness. We are passengers on this magnificent spaceship Earth, and like any complex vehicle, it has its own internal mechanics, its own cycles of stress and release. To ignore these fundamental truths is to invite surprise when the ground next shakes with ferocity. The Earth has a long memory written in its rocks and fault lines. It patiently accumulates energy over centuries, sometimes millennia, preparing for its next grand and often terrifying display of power. So we must ask ourselves, are we listening to what the Earth is telling us? The subtle tremors, the historical records, the scientific data, these are all whispers from our planet. They speak of a restless interior, of pressures building, of an energy that must eventually find an escape. Megaquakes are a stark reminder of our place in the cosmos, on a planet that is beautiful, powerful, and at times incredibly dangerous. They are a natural process, as much a part of Earth's story as the formation of stars is to the universe's. Understanding them is key to our continued journey. What exactly is a megaquake? The term itself sounds formidable, and rightly so. Scientists use the moment magnitude scale to measure the energy released by an earthquake. A megaquake is generally considered to be an earthquake with a magnitude of 8.0 or higher. These are not your everyday rumbles. These are colossal events that can rupture the Earth's surface for hundreds of kilometers. The energy they unleash is difficult to comprehend. Think of thousands of atomic bombs exploding simultaneously. That gives you a sense of the sheer power we are dealing with. This energy doesn't just shake the ground, it can liquefy it, trigger massive tsunamis, and cause widespread destruction. The primary culprits behind these colossal events are tectonic plates. Imagine the Earth's outer shell, its lithosphere as a cracked eggshell. These cracked pieces are the tectonic plates. They float on the semi-fluid asthenosphere beneath them. Where these plates meet, we find fault lines. Most earthquakes occur along these boundaries. In the case of megaquakes, we are often looking at a special type of plate boundary subduction zones. Here, one tectonic plate, usually a denser oceanic plate, dives beneath another, less dense continental or oceanic plate. This process is not smooth. It's a cosmic struggle of immense pressure and friction. As one plate grinds its way downwards, the edges can become locked. The overriding plate gets stuck, but the relentless motion of the underlying plate continues. This causes the overriding plate to slowly deform, to bend and bulge, storing an incredible amount of elastic energy like a compressed spring. For decades, even centuries, this silent tension builds. The rocks strain, approaching their breaking point. Then suddenly the locked section gives way. The accumulated energy is released in a matter of minutes or even seconds. The overriding plate snaps back into place, unleashing powerful seismic waves that radiate outwards in all directions, causing the ground to shake violently. This sudden release creates the primary shaking of a megaquake, but the story doesn't end there. The movement of the seafloor in a subduction zone megaquake can displace enormous volumes of water. This is what generates tsunamis, giant ocean waves that can travel across entire ocean basins at the speed of a jetliner. These waves can be imperceptibly small in the deep ocean, but can grow to devastating heights as they approach shallow coastal waters. So a megaquake is not just about the shaking, it's about a cascade of interconnected natural hazards that can affect vast areas far beyond the immediate rupture zone. To truly understand megaquakes, we must journey deeper into the theory of plate tectonics. This theory revolutionized our understanding of the Earth in the 20th century. It provides the framework for explaining not just earthquakes, but also volcanic activity, mountain formation, and the very distribution of continents and oceans. Our planet's lithosphere is not a single unbroken shell. Instead, it's divided into about a dozen major plates and many more minor ones. These plates are like giant irregular pieces of a global jigsaw puzzle, constantly in motion, driven by the heat escaping from the Earth's core. The movement of these plates is slow, typically only a few centimeters per year, about the same rate your fingernails grow. But over geological timescales, this slow, steady movement reshapes the face of our planet. There are three main types of plate boundaries defined by how the plates interact. At divergent boundaries, plates move apart and new crust is formed as molten rock rises from the mantle. At convergent boundaries, plates collide. This can result in one plate diving beneath another, subduction, or both plates crumpling upwards to form mountain ranges like the Himalayas. Lastly, at transform boundaries, plates slide horizontally past each other. Megaquakes, as we've seen, are most commonly associated with convergent boundaries, specifically subduction zones. These zones are places where immense forces are locked in a titanic struggle. The Pacific Ring of Fire, for example, is largely defined by a series of subduction zones. Here, the Pacific Plate and other smaller plates are diving beneath continental plates. The friction and stress that build up in these zones are the primary ingredients for the world's largest earthquakes. The sheer scale of these interacting plates means that when they finally slip, the area affected and the energy released are enormous. Understanding plate tectonics allows us to identify regions at high risk. It's like knowing where the seams are on a slowly tearing piece of fabric. The seams are where the stress concentrates and where the eventual rip is most likely to occur. Scientists use GPS technology to measure the movement of plates with incredible precision. This data helps them understand which fault lines are accumulating stress and how quickly. While it doesn't allow for exact prediction of when an earthquake will happen, it provides crucial information about where the potential for large earthquakes is greatest, guiding our efforts in hazard assessment and preparedness. When we talk about regions most likely to be hit by a megaquake, one area stands out above all others: the Pacific Ring of Fire. This is not a literal ring of fire, but rather a vast horseshoe-shaped zone that stretches for some 40,000 kilometers or 25,000 miles around the Pacific Ocean basin. It runs up the western coasts of South and North America, across the Aleutian Islands of Alaska, down the eastern coasts of Asia, encompassing Japan and the Philippines and looping through Indonesia and New Zealand. This immense arc is the undisputed champion of seismic and volcanic activity on our planet. Why is the Ring of Fire so active? It all comes down to plate tectonics. This region is where the massive Pacific Plate interacts with numerous other smaller tectonic plates, including the North American Plate, the Eurasian Plate, the Indo-Australian Plate, and the Nazca Plate. Most of these interactions involve subduction, where oceanic plates are forced beneath continental plates or other oceanic plates. These subduction zones are the perfect breeding grounds for megaquakes. The immense pressure, the friction, the locking of plate boundaries, all the necessary conditions are present in abundance along this vast perimeter. Approximately 90% of the world's earthquakes and about 81% of the world's largest earthquakes occur along the Ring of Fire. It's also home to more than 75% of the world's active and dormant volcanoes. Countries like Japan, Chile, Peru, Mexico, the western United States, especially California, Oregon, Washington, and Alaska, Canada, Russia, Indonesia, and New Zealand all lie within this volatile zone. For the millions of people living in these regions, the threat of a major earthquake is a constant reality, a part of life that shapes their building codes, their emergency preparedness plans, and their collective consciousness. The historical record of the Ring of Fire is a litany of catastrophic events. The 1960 Valdivia earthquake in Chile, the largest ever recorded at magnitude 9.5, occurred here. So did the 2004 Indian Ocean earthquake, magnitude 9.1 to 9.3, which triggered devastating tsunamis, and the 2011 Tohoku earthquake in Japan, magnitude 9.0 to 9.1, which also led to a catastrophic tsunami and the Fukushima nuclear disaster. These events serve as stark reminders of the immense power lurking beneath the ocean and along the coasts of the Pacific. The question for these regions is not if another megaquake will strike, but precisely where and when along this vast, restless boundary. Section 5. Beyond the Ring, Other Hidden Fault Lines. While the Pacific Ring of Fire deservedly gets the most attention for its seismic activity, it is not the only place on Earth where megaquakes can and do occur. Other regions also harbor significant fault systems capable of generating powerful earthquakes, sometimes in areas that might seem less obviously prone to such events. Understanding these other zones is crucial for a complete picture of global seismic risk. These areas might not experience megaquakes with the same frequency as the Ring of Fire, but the potential for devastation is just as real when these sleeping giants awaken. One such significant zone is the Alpide Belt, which extends from the Mediterranean region eastward through Turkey, Iran, and the Himalayas into Southeast Asia. This belt is the result of the collision between the northward-moving African, Arabian, and Indian plates with the Eurasian plate. The Himalayas themselves are a product of this colossal continental collision. This ongoing crunching and grinding of continents generates immense stresses, leading to powerful earthquakes. Historically, this region has seen devastating quakes, such as the 2005 Kashmir earthquake, which had a magnitude of 7.6, and the 2015 Nepal earthquake with a magnitude of 7.8, both of which caused widespread destruction and loss of life. Even within continents, far from active plate boundaries, large earthquakes can occur. These are known as intraplate earthquakes. While less common than plate boundary earthquakes, they can be particularly dangerous because these regions are often less prepared. The New Madrid seismic zone in the central United States is a prime example. In the winter of 1811 to 1812, this zone produced a series of powerful earthquakes, estimated to be magnitude 7.0 or higher, that were felt over vast areas and even rang church bells in Boston. The causes of such intraplate seismicity are still being researched, but often involve ancient, deeply buried fault systems that are reactivated by stresses transmitted from distant plate boundaries. Other areas of concern include the East African Rift Valley, where the African continent is slowly splitting apart, creating new divergent plate boundaries. This rifting process is associated with volcanic activity and earthquakes. The Caribbean plate, nestled between the North and South American plates, also has complex fault systems capable of producing large quakes, as tragically demonstrated by the 2010 Haiti earthquake, which had a magnitude of 7.0. So while the Ring of Fire is the primary hotspot, the Earth's restlessness is far more widespread. Vigilance and scientific study are needed across many different geological settings to understand and prepare for the planet's powerful tremors. Section 6. When the Ground Roared. Lessons from past cataclysms. History is a profound teacher, and when it comes to megaquakes, its lessons are written in shattered cities and altered landscapes. By studying past events, we gain invaluable insights into the behavior of faults, the types of hazards megaquakes produce, and the vulnerabilities of human societies. Each major earthquake is a natural experiment, providing data that helps scientists refine their models and engineers design safer structures. The echoes of past cataclysms remind us of the raw power of our planet and the importance of heeding its warnings that are often centuries, if not millennia, in the making. Consider the 1700 Cascadia earthquake, an event that occurred along the Cascadia subduction zone stretching from northern California to Vancouver Island. There were no written records from the region at that time to describe the earthquake itself. However, meticulous geological research, including studying tsunami deposits in North America and precise tsunami records in Japan, has allowed scientists to reconstruct this event. They now know it was a megaquake of approximately magnitude 9.0. This ghost earthquake story highlights how science can uncover past events and reveal the immense long-dormant threat in regions like the Pacific Northwest of the United States and southwestern Canada. Further back in time and across the globe, the 1556 Shanxi earthquake in China, though not a subduction zone megaquake in the typical sense, its magnitude is debated but was likely around 8.0, stands as perhaps the deadliest earthquake in recorded history. It is estimated to have killed around 830,000 people. This event underscores that immense devastation can occur even from quakes that might not reach the megaquake threshold of magnitude 9.0, especially in densely populated areas with vulnerable construction. It highlights the crucial role of building practices and local geology in determining the impact of an earthquake. More recently, the 2011 Tohoku earthquake in Japan, a magnitude 9.0 to 9.1 event, provided a wealth of modern data. The earthquake itself was devastating, but the subsequent tsunami caused the most catastrophic damage, including the Fukushima Daiichi nuclear disaster. This event showed that even a country as well prepared as Japan could be overwhelmed by the scale of a true megaquake and its cascading consequences. It led to a global re-evaluation of tsunami risks and nuclear power plant safety. These historical events, from Cascadia to Shanxi to Tohoku, are not just tragic stories, they are critical data points in our ongoing quest to understand and live with our dynamic Earth. Section 7. Listening to the Earth, what the experts foresee. Scientists who study earthquakes, known as seismologists, are like detectives, constantly searching for clues that the Earth provides. They use a variety of sophisticated tools and techniques to monitor fault lines, measure crustal deformation, and analyze past earthquake patterns. While precise prediction of the exact time, location, and magnitude of a future earthquake remains an elusive goal, experts can make probabilistic forecasts. These forecasts assess the likelihood of an earthquake of a certain size occurring in a specific region over a given period, often decades. These are not crystal ball predictions, but rather scientifically grounded assessments of risk. For the Cascadia subduction zone in the Pacific Northwest, experts estimate there is a significant probability of a megaquake, magnitude 8.0 or higher, occurring in the coming decades. The last major rupture was in 1700, and the average recurrence interval for such events in this zone is thought to be between 200 and 800 years. We are currently within that window. A Cascadia megaquake could cause widespread shaking from Northern California to British Columbia, trigger a massive tsunami hitting the coast within minutes, and lead to prolonged disruptions to infrastructure and daily life for millions of people. In California, the San Andreas Fault is a major concern. While it is a transform fault, not a subduction zone, it is capable of producing very large earthquakes, around magnitude 8.0. Experts believe there is a high probability of a major earthquake, often referred to as the Big One, striking Southern California along this fault within the next 30 years. Similarly, the Hayward Fault in the San Francisco Bay Area is considered one of the most dangerous faults in the United States due to its proximity to dense urban populations and the high likelihood of a major rupture. Other regions like Japan, Chile, and Indonesia remain on high alert due to their position on the Ring of Fire. Japanese seismologists, for instance, constantly monitor the Nankai Trough, another subduction zone with a history of recurrent megaquakes. Experts suggest that the next major Nankai Trough earthquake is overdue. These expert opinions are not meant to cause panic, but to foster awareness and drive preparedness efforts. They are a call to action, urging communities, governments, and individuals to take the threat seriously and to invest in measures that can save lives and reduce damage when the inevitable occurs. Section 8. The quest to predict science on the front lines. The dream of accurately predicting earthquakes, specifying when, where, and how large they will be, has captivated scientists for generations. Imagine the lives that could be saved, the damage that could be mitigated if we had a reliable early warning system. However, despite decades of intensive research and significant advances in our understanding of earthquake processes, precise, short-term prediction remains largely beyond our current scientific capabilities. The Earth's crust is an incredibly complex system, and the processes leading up to a major rupture are hidden deep beneath our feet, making them extremely difficult to monitor directly. Scientists have explored various potential precursors, such as changes in groundwater levels, emissions of radon gas, unusual animal behavior, and small foreshocks. While some of these phenomena have occasionally been observed before some earthquakes, none have proven to be consistently reliable indicators. The problem is that these signals can also occur without a subsequent earthquake, or major earthquakes can strike without any discernible precursors. The sheer variability and complexity of fault systems mean that what might precede one earthquake may not precede another, making universal prediction methods very challenging to develop. Despite the challenges of short-term prediction, science is making significant strides in other areas. Earthquake early warning (EEW) systems are a promising development. These systems do not predict earthquakes before they happen. Instead, they detect the initial, less damaging P waves, primary waves, that travel faster than the more destructive S waves, secondary waves, and surface waves. Once an earthquake has started, these systems can provide a few seconds to tens of seconds of warning before the strong shaking arrives. This brief window can be enough time for people to take cover, for automated systems to shut down gas lines, stop trains, and secure critical infrastructure. Furthermore, long-term forecasting based on paleoseismology, the study of past earthquakes, GPS measurements of plate motion, and sophisticated computer modeling, is continually improving. This helps us understand which faults are most hazardous and how often they might rupture. This information is vital for developing building codes, land use planning, and public education campaigns. So, while the holy grail of exact prediction remains elusive, scientific efforts are providing increasingly valuable tools and knowledge to help us coexist more safely with our seismically active planet. The quest continues, driven by the profound human desire to understand and protect ourselves from these powerful natural events. Section 9. Our cosmic address, adapting to a dynamic world. We live on a planet that is constantly reshaping itself. Megaquakes are a dramatic, sometimes terrifying expression of Earth's inner dynamism. They are not malicious acts of nature, but rather fundamental processes that have sculpted our world over eons. From the highest mountain ranges to the deepest ocean trenches, the fingerprints of tectonic forces are everywhere. To wish for a world without earthquakes would be to wish for a geologically dead planet, a world unlike the vibrant, evolving home we know. Our challenge, then, is not to stop these immense forces, but to understand them and learn to live more wisely in their presence. Preparedness is our most powerful shield against the inevitable. This begins with knowledge, understanding the specific risks in your region. It involves robust building codes, ensuring that our homes, schools, hospitals, and infrastructure are designed and constructed to withstand strong shaking. Retrofitting older, vulnerable buildings is a critical investment. It means developing comprehensive emergency plans at the individual, community, and national levels. This includes securing essential supplies, knowing evacuation routes, and practicing earthquake drills. It's about fostering a culture of resilience where communities can recover and rebuild more effectively after a disaster. Staying informed is equally crucial. Scientific agencies around the world continuously monitor seismic activity and update hazard assessments. Public education campaigns play a vital role in disseminating this information and teaching people how to protect themselves. Awareness of earthquake early warning systems, where available, and knowing how to react when an alert is received can make a life or death difference. It's about transforming fear into proactive engagement, replacing anxiety with a sense of empowerment that comes from knowing what to do. The Earth will continue to shake, but our response to that shaking is within our control. Ultimately, understanding megaquakes is part of understanding our place in the cosmos. We are inhabitants of a specific planet, with its own unique set of rules and behaviors. Just as we learn about the weather patterns or the changing seasons, we must learn about the geological rhythms of our world. The next megaquake is not a vague possibility, but a future certainty for some parts of our globe. By embracing scientific knowledge, investing in preparedness, and fostering a global commitment to resilience, we can face this certainty not with dread, but with the quiet confidence that comes from being prepared for the awesome power of our ever-changing, ever-active Earth.